Welcome students. We are going to talk about mechanical and electrical vibrations. Linear second order differential equations with constant coefficients serve as a mathematical model for a lot of physical processes, including the electrical and mechanical oscillations. And many of these can be formulated as an initial value problem, a to y double prime plus by prime plus cy equals to g of t, where y of 0 is y naught and y prime of 0 is y0 prime. So this is a second order linear differential equation with initial conditions given. Okay. So let's see one of the applications, which is about motion of a mass on the spring. So here we have a spring of length L. So let this length be L. Now to this spring, let's attach a mass M. So you will have the same spring will get elongated. So the spring gets stretched. This is mass M. Suppose the original length was here. So we have, this was our original length L, and it got elongated by L. And then of course, then after that, so the spring got elongated, and then suppose there is a motion happening. So again, there is a change in the, so the spring is moving up and down because of the mass M. So let me write down, let L be the initial length of the spring, the length of the spring. M be the mass of the object attached to the spring now. Now this will cause an elongation L here, this L, elongation L. So this is your lengthening or elongation caused by M. And so once this stretching by L happens, that is what is called as equilibrium position, and any motion beyond that is what we'll call as displacement. So U be the displacement past of the object past the equilibrium position. So that is a setup now. So the idea is you have a string of length L. You basically put a mass on it, mass M attached to it, and then it causes the elongation, and then there is some motion happening, which is basically given by displacement U. So we want to understand this motion of mass on the spring. So suppose that the system is in equilibrium. That means all the forces are balanced out. Yeah. So in that case, what will happen? So there are two forces which are acting on the object primarily. One is the gravity, So the gravity is acting on the object. Let's call that force Fg, which is mass times gravitational acceleration, which is acting downward. Downward. And now once the spring gets stretched, of course, it will try to pull it back up, right? So then the second force, which is acting on the spring, so spring exerts an upward force, a force upward. Good. And that is given by Hooke's law. What does Hooke's law tells us? That the force on the spring, the force exerted on the mass due to spring is proportional to the length of the elongation. So it's going to be minus k times L, where k is constant. K is called Hooke's constant, and this is because of Hooke's law. Hooke's law. So the idea is you have an object M. It has two forces acting on it. One is upward because of the spring, which is minus KL because of Hooke's law, and downward is the gravity, which is Fg. Okay, so these are the forces acting on it. Yeah. So K is the constant. I mean, K is Hooke's constant, or K is also called spring constant. Is the spring constant. Now, what happens in equilibrium? In equilibrium, both of these forces will cancel out each other, right? So in equilibrium, the forces are balanced. The forces are balanced out. So that would mean if we add the force here, it will be basically 0. So that is mg minus kl is 0. Or this gives me k equals to mg over L. It gives me a way to measure the spring constant, which is mg over L. So what happens in the equilibrium position? So the equilibrium position is a position L plus L, where L is the length of the, where L is the length, or the initial is the length of the spring, and satisfies, and this satisfies what? L plus, it satisfies this part here, that is mg minus k L equals to 0. So this is the equilibrium state, no motion happening here. Now, let's consider the dynamic problem. That means there's some change happening. And what is this change? The dynamic problem is when the object is initially displaced or acted by an external force. So you can take this object here and you can basically act on it by an external force, or the object is displaced. So once you displaced it from the equilibrium position, so let u equals to ut be the displacement from the equilibrium position at time t. So from the equilibrium position means what? From here onwards. Okay, so this will be your u. So let u equals to ut be the displacement from the equilibrium position time t. Now let's see what are the forces acting on your on your mass m. So basically there are one force which is acting is the gravity, which is pulling it down. So it's pulling it down. So it's going to be F equals to mg. Now the spring force is, again by Hooke's law, is K times length L, which is L plus ut, right? Because now the length is not just u, sorry, the length is not just L, but it is the whole thing now from here to here. So it's L plus u. Now, viscous damping, normally viscous damping happens when you are due to the air friction. Okay, so viscous damping again is in the opposite direction. So normally due to air friction, due to air resistance or friction. Here lambda is called the damping constant. And then there could be an external force. Think about it. There could be a force which acts on the object, like either periodically or often. Okay. Yeah. So it could be because due to the motion of support or whatever. Right. Now all this leads to, so all combination of all these forces lead to a motion. All right. So combination of all these forces is what gives us the motion. So mu double prime is equal to Fg, because mass into acceleration, that is Newton's law, right? So mass into acceleration is the force, and that force is sum of all these forces, Fg, Fs plus Fd plus F. So that is going to be mg minus k L plus u minus lambda u prime t plus a force F. We don't know what that force is. It could be any external force. Now, if you organize this, you get mg minus kl plus k minus, my bad, minus k u minus lambda u prime t. Sorry, gamma, it's called gamma. This constant is called gamma plus f. Now, if I reorganize it, I get, so this will be what? This is 0. Why? Because of the, this is the thing coming from the equilibrium position here. So what do we get? Let's reorganize it a bit. So m u double prime plus gamma mu prime t, or just mu prime, plus k mu equals to f of t. Okay, so this is what we got. So this gives us the equation of motion for the object attached to the spring. All right. The only thing which is unknown in some sense is the forcing function. Now, typically you're given two initial conditions, namely you're given u of 0 is sum u naught, and u prime of 0 is sum v naught. So these are, so an initial displacement and initial velocity is given to you. So this captures your motion of the spring. Okay. Now we want to study this kind of differential equations because they come from certain important physical phenomena. So let's consider a few cases and work this out. So the first case is what is called as simple harmonic motion. Now in simple harmonic motion, you have this f of t, this becomes 0, and there is no damping. That means gamma is 0 as well. So let's write that down. So we have f equals to 0 and gamma equals to 0. So how does your differential equation become? So let me just rewrite the same thing from top there. So I will get m u double prime. So I'll get m u double prime. So gamma is 0 plus ku equals to 0. Now we want to solve this. Note that m and k are constants. So the characteristic equation is m r square plus k equals to 0. This gives us r equals to k by m square root with a plus or minus I sign. Okay. So now just for the sake of brevity, just to have a short representation, we'll have, so what are the solutions here? So let's call this as, so just for the sake of short writing, let's write omega naught as k by m. So then your r becomes plus or minus I omega naught. And you already know what is the solution to this. So the solution to this is given by ut equals to a cos omega naught t plus b sine omega naught t. So this is the solution we got for this differential equation. Okay, so harmonic motion. However, we prefer to write it in slightly different format. We prefer to write it in the form of, it is preferred to write it in the form r cos of omega naught t minus delta. Now, why do you write it in this form? See, if you write it in this format, you can read, so if you write this equals to your u of t, you can read how the function is. It's basically that it's like cosine with certain period, certain amplitude, and certain phase. So let's see how do we get, so if I want to write it in this format, what is my r? So question is, r is what? Delta is what, right? Because we got omega naught from the previous one. So let's expand this. So what is cos of a minus b? So cos of a minus b is cos a cos b plus sine a sine b. So if I want to write this thing as r of cos omega naught minus delta, then what do I get? This is going to be r cosine of delta times r cosine, sorry, not r is outside, so cosine of omega naught t plus r sine of delta times sine of omega naught t. Now let's do the comparison. So if we compare, what should we get? We have this a, we have b, right? So this a should be equal to this guy here, and this b should be equal to this thing here. So let's work that out. So we get what? We get R equals to, so R cos, so now we want to find out, so what do we need to find out? R and delta. So R cos delta is A, R sine delta equals to B. So this gives me, if you square them and add, you'll get R square equals to A square plus B square. So this gives me R equals to square root of A square plus B square. Note that this A and B are fixed because of what? Because it's an initial value problem. Yeah, right? Because it's basically an initial value problem here, right? So A and B must be fixed by the initial value, initial conditions. Now let's work on it a bit more. So we get now, so what is delta? So for that, to figure that out, divide B by A. So R sine delta over R cosine delta equals to B over A, which is equal to tan of delta. That means your delta is tan inverse of B over A. So now we get this. So we get omega naught is K over M. We choose to call it as that is called the natural frequency. And your delta is called phase and R is called amplitude. Why? Let's draw the picture. So this is how it will look like, right? So initially, yeah, so you have what? R of cosine of omega t minus delta. At time t equals to 0, at t equals to 0, you are have what? R of cosine of minus delta, but cosine is an cosine is an even function, which is going to be cos of delta. So you see at time t equals to 0, this width is R cosine delta. Now, basically you should think about this as cosine of omega naught t multiplied by R, so the amplitude increases, and then minus delta is the phase difference, right? So what happens is you can think about this as the following. Your cos, you're starting with your cos t. You are basically making it into cos of omega t because you're changing the period. Then you're either multiplying by the amplitude if you wish to get R of cos omega naught t. And then you do minus delta to shift the phase. So this is your phase shift. Yeah. So instead of starting, so because cosine starts like that, right? So now that got shifted by delta. Okay. So this is the setup, and the frequency is omega naught. Okay, so let's work with an example here now. So object of mass m, so m is 4, is attached to a spring with a spring constant k. It is then stretched 10 centimeter from the equilibrium position and set into motion with the initial velocity of 130 centimeter. Assuming there is no damping, no external force, find the frequency, amplitude, and phase of oscillation. So first of all, there is no, so point to note is that there is no damping and no external force. So it will be like a simple harmonic motion. So this is the case where there's no external force and no damping. So it's going to be a form. So this is a form u of t satisfies what m u double prime plus k u equals to 0, right? Now we need to find m. So m is 4, k is, now you have to see if the constants match, right? It's not one with a kilogram and the other one is with something else. Both are kilograms, so that's fine. So k is going to be 169. So m is 4 kg. Let's write it properly. M is 4 kilograms. K is 169 kilogram per second square. So what do I get out of this? So my damping is 0 and external force is also 0. So no external force, damping, gamma is 0. So what is my equation of motion? M u double prime, so 4 double prime plus 169 u equals to 0 is your differential equation. Now you need to find the initial conditions. So what is the initial condition? Initially it is stretched 10 kilometers, sorry, 10 centimeters, my bad, from the equilibrium position. So your initial displacement is going to be 10 centimeter and initial velocity is 130 centimeter per. So u prime of 0 is also provided to you, 130 centimeter per second. Now you have everything you need. We can go ahead and solve this differential equation. So that's the first step, to find out the differential equation. Second step is to basically find the general solution. So what is the general solution given by? So first we need to compute omega naught, which is square root of k by m, which is going to be, what is square root of k? So k is 169, m is 4, square root of this, which is 13 by 2. This is your, right? And if you look at this, it's going to be, what is the unit of this? So kilogram gets cancelled. You are with what? By 1 by second, right? So this is going to be per equals to 13 by 2 per second. So this is your frequency, right? Now, what is your u of t? So the equation is given by u of t equals to a cosine 13 by 2t plus b sine 13 by 2t. Again, what is our goal? Our goal is to describe the what the amplitude, the phase and the frequency, right? Because that's what is asking us here. Find frequency, which is omega naught, amplitude is r, and phase of oscillation is delta. So first we need to write it in the form of r cosine of omega naught t minus delta. So this is the format we want to write it down in. So now we need to find a and b. So for that we'll apply the initial condition. So u of 0 on one hand is given to us as 10. So on one hand, this is given to us as 10. On the other hand, this is, when you put it in the formula, you get a cosine 0, which is 1, plus b sine 0, which is 0. So a equals to 10. That's what you get right away. So a times, I can write a times cos 0 plus b times sine 0. This implies a equals to 10. Now we need to find out our b. So for that, notice that if you take derivative u prime t, on one hand you get what? 13 by 2 a sine 13 by 2 t with a minus sign plus 13 by 2 b cosine 13 by 2 t. So this implies u prime of 0. So what do we get? U prime of 0. On one hand, it's given to us as 130. And on the other hand, this is going to be, So when you put 0, it gets minus 13 by 2 times a sine 0 plus 13 by 2 b cosine 0. So this implies 130 equals to 13 by 2 b cosine 0, and this gives you your b is 20. So now we got that, we need to find out. So step 4, find r and delta. So what is your r? R was square root of a square plus b square. So what do we get out of that? This is going to be square root of a was 10, right? A is 10, b is 20. So 10 square plus 20 square, which is going to be, take 10 common, you're left with in bracket 5. So 10 square root of 5. This is your r, and delta is, so tan delta is b over a, which is 20 over 10, which is 2. So this means, what this means, delta equals to tan inverse of 2. And so since tan is positive, there are two possibilities. Either delta belongs to 0 to pi by 2, that's where the delta tan is positive, or delta belongs to pi to 3 pi by 2, right? So this is a possibility now, but a and b both are positive. Since a and b are both positive, which are positive, both positive, this implies the sine and cosine is also positive, right? So sine delta and cosine delta are also positive. This implies what? This implies the only possibility for your delta to come from is from this part here. This implies delta comes from this part, and in fact you can see that delta equals to arctan 2, which comes out to be roughly 1.01, sorry, 1.1071, something along those lines. And you get u of t is this guy, your r times cos of omega naught t is 13 by 2t minus the phase, which is going to be 1.07. So this is your solution to the whole problem. So what was this case? This was a case of simple harmonic motion. And what is your simple harmonic motion? The simple harmonic motion is when there's no damping, no external force. So you see that it will keep perpetually going like this, right? So the motion will be like a spring, up and down, up and down, up and down, and there will be nothing, there will be no change in it. It will be constantly going up and down, up and down, up and down. But in real life scenario, that doesn't happen, right? If you pull a spring, it will go up and down, but it will stop eventually. So let's see what happens in that case. So we have the concept of damped harmonic motion. So now we'll we'll now try to include the effect of dampening. So that means what? The gamma, again, go back to this equation. What is the differential equation we have? We have this differential equation, and in this case, we'll assume that there's a dampening. That means gamma is non-zero, but f of t, the forcing function, is still 0. So gamma is non-zero, so the differential equation becomes m u double prime plus gamma mu prime plus ku equals to 0. Again, these are constant coefficients. M, gamma, k are constants. So the characteristic equation is m r square plus gamma r plus k equals to 0. Now the two roots, so let's solve it using quadratic formula. So with roots, what are the roots? The roots are r1 and r2 given by minus gamma plus or minus square root of b square. So b is gamma, so minus b plus or minus b square, which is gamma square, minus 4a, which is m, c, which is k here, divided by 2a, which is 2 times m. All right, now how do you find out the roots of this? So the deciding factor is this part here, right? Because if this is the inside of the square root is positive, then you'll have two distinct roots. If inside of square root is 0, then there will be exactly one real solution. And if inside of the square root is negative, then there will be exactly what? There will be complex conjugate roots. So let me write that down. So if gamma square minus 4mk is less than 0, this implies what? Gamma square is less than 4km. That means if you take the square root on both sides, you'll get gamma is less than square root of 4km. Then we have complex pair of roots. If gamma equals to km, this part will become 0. And in that case, we will have exactly one root which is repeated. However, if gamma is greater than 4km, then we'll have two distinct roots. Okay, so let's analyze each case one by one. So case 1, when we have complex set of roots. So what do we have when we have complex roots? So then the general solution is given by u of t equals to, now how do you write such complex set of roots? You have e to the power, the real part. What is the real part? Minus gamma by 2m. So remember, if you had solution r was lambda plus mu I plus or minus mu I, the solutions were of form e to the power lambda t sine of mu t, actually sine of mu t times a plus b times cos of mu t. Yeah, this was your general solution, right? For the complex roots for the characteristic equation. So what is the solution going to look like? So e to the power minus gamma by 2m t a cos of mu t plus p sine of mu t. Now what is my mu? Instead of writing this whole thing as again and again, where I'm going to write short mu equals to 4 km minus gamma square upon 2m, right? Just to write that in the short format. So now now we need to find out what a and b is, right? So we need to write down letting a equals to r cos delta and b equals to r sine delta for some suitable r and delta, for some suitable r and delta. What do we get? We get mu, sorry, u of t is r e to the power minus gamma by 2m t times cos of mu t minus delta. Now let's try to analyze it. Let's not worry about finding r and delta right now. Sorry, r and delta right now, but think about it. So let's see this part here. So this is, if you look at cos t, mu minus t, it's gonna basically look something like that, yeah, periodic. However, because of this component here, as t goes bigger and bigger, the value of this is going to go lower and lower. So basically what it does is it creates a dampening effect like that. So what happens is your amplitude, so with as t goes on, your amplitude is also decreasing. So you get this kind of amplitude, and then your motion is getting smaller and smaller, right? Eventually it will basically lead to what? Zero. Now note, in this case, we can't call mu as a frequency because it's not going up and down with, it's not following mu as the periods, right? So what we'll do is we'll call mu as quasi-frequency, right? Generally, if you just had r cos of mu t, then what do you have? You have 2 pi is equal to, so the period becomes what? It repeats after 2 pi, so you'll have 2 pi equals to mu t. So you basically find the connection between mu and t using this guy. But in this case, it's quasi-frequency. Why? Because also the amplitude is changing, right? So this whole thing is changing over a period of time. Now, let's compare it with undamped case. So what about undamped case? Compare. So what is it? Let's compare with undamped case. So how do we compare? We'll basically take mu and divide it by omega naught to see what kind of relation do they have. Omega naught comes from the undamped case, right? So it was square root of k by m, and this guy is square root of 4 km minus gamma square divided by 2m. And if you simplify this, this is going to be square root of 1 minus gamma square by 4 km, which is roughly, for very small x, this is roughly going to be 1 minus gamma square of 8k. Yeah. This is some kind of a Taylor expansion, right? So now what do you notice from here? So if your gamma square is less than, it's very small compared to 4 km, this is what it means. This implies what? Small dampening reduces what? The frequency of oscillation. So this is what is happening. So if gamma is really small compared to 4m, this will be roughly 1, right? That means what? That means mu and gamma naught are going, sorry, mu and omega naught are going to be roughly the same. Now let's deal with this next case. So in this was a case when the roots were what? The complex roots. The roots were complex conjugates of each other. Let's consider the next case when the roots are what? Real and repeated. So in that case, what you'll have is the solutions will be of form ut is going to be a plus, so one solution is going to be, so in that case, what do you get? You get 4 km minus mu square is 0. So the solution is going to be r is, so you start with mu double prime plus k mu prime plus ku equals to, so lambda mu prime, sorry, my bad, what am I saying? So we have m u double prime plus gamma u prime plus k u equals to 0. And if we have repeated roots, the roots are going to be of form what? Minus gamma divided by 2m. And if you recall, then we have to multiply. So one solution is going to be e to the power gamma by 2mt, and the other solution is going to be t times e to the power gamma by 2mt. So if I combine and write them together, I will have a b e to the power minus gamma by 2m multiplied by t for some constant a and b, which is to be determined by the initial condition. Now suppose you have initial condition as what? U of 0 is half, u prime of 0 is 7 by 4. Yeah, in that case, what is your differential equation? Your differential equation is u double prime plus u prime plus 1 by 4 u equals to 0. In that case, you can see what happens is basically it takes one oscillation, but then it goes down. It doesn't oscillate anymore. So this is a critical dampening. The solution no longer. So this solution has critical dampening. That means what? Solution no longer oscillates. Okay. Now consider the next case, which is two distinct real roots. So this leads to an overdamping. So what do we have? You have u of t equals to a e to the power r1t plus b e to the power r2t, and in r1 and r2 both are less than 0. And we have, since, why is this both less than 0? So think about it. We have mu double prime plus gamma mu prime plus k u equals to 0. So now if you have a solution, say if you have an equation where x squared plus 2, or say x squared plus 2x, no, well, let's say 2x or 3x plus 2. So this guy is positive, this is also positive. So, well, if you have an equation like this, all the roots, both the solutions are going to be negative, right? So that's why, since these guys are positive, so since they are greater than 0, we get R1 and R2 are less than 0. Since what? Gamma and K are greater than 0. Yeah. And what happens to the u of t then in that case? So if you look at this, then if R1 and R2 are greater than R1 and R2 both are less than 0, then ut will go to 0 as t goes to infinity, right? Because this is with the negative power. So this guy is with negative power. This guy is with negative power, right? So they will both go to 0 as t goes to infinity. So for example, look at this, e to the power minus 2t or minus 3t. So you see, it basically, there's an over dampening. There's not even a single oscillation. The whole solution is driven down to what? 0. So this is the scenario of motion of spring under damping. Okay, so in this lecture, what have we done? We have tried to understand the mechanical vibration of a spring, And the mechanical vibration of the spring basically led us to the following differential equation here. And here in this work, we have assumed that the external forcing function is 0. And then we got the case when gamma is 0, we solved it, we got simple harmonic motion. If gamma is not 0, then there's a dampening happening. Now, those dampenings are of three kinds that depend on the solution to your differential equation, solution to your differential equation, namely solution to your characteristic equation actually. So in that case, if gamma was less than equal to 4km, you had a complex conjugate roots, and that led to, again, dampening is happening, but with an oscillation. So this is a damped oscillation. Why? Because the oscillation is happening, but it's getting damped. Damped in some sense is to get reduced. Then if you had both the roots were same for the characteristic root, you got u of t to be the following, which is basically the case where there's one oscillation, but then goes down, right? So this is critical dampening. And if there are two distinct real roots, then there's over damping. The solution is just driven down to what? Driven down to 0 right away, like that. Okay. And again, the underlying idea is that both R1 and R2 are going to be less than 0 because of gamma and K. Thank you for your attention.